This video is on the kind of the second part of the applications of equilibrium constants. So the prior video was the video discussing how we determine if a reaction is at equilibrium, and then how we determine how a reaction will proceed if it's not at equilibrium, and that was the whole discussion of calculating the reaction quotient Q, capital Q, and predicting if the reaction would proceed from left to right and create more products, or if the reaction would proceed from right to left and create more reactants. So that was the first part of kind of this section. And the second part of this section is, we're on the second page, calculating equilibrium constants, or concentrations, I'm sorry. And we're going to do that with equilibrium data and then without equilibrium data. So actually, this first part of calculating equilibrium concentrations with equilibrium data is something we've already done in practice. But here's an example, and it's pretty simple. It says for the formation of ammonia, of course, our favorite reaction, Kp is equal to 1.45 times 10 to the negative fifth. And an equilibrium mixture of the three gases, the partial pressure of H2 and N2 are given, and then it wants to know what's the partial pressure of the ammonia at equilibrium. So probably first idea, of course, is to write the reaction. So the famous Haber process here. So N2 and H2 creating ammonia. They tell me that Kp is known. Again, this is old information. Knowing this this value of the reaction. The equilibrium constant is very small. It's less than 1. We know that this is a reactant-favored reaction, the way that this is written. So, okay, so they tell me that at equilibrium, I know the partial pressure of this, and I know the partial pressure of this, and I'm interested in finding the partial pressure of this. So, initially, your gut might say maybe I need an ice chart, but they're telling me that at equilibrium, I know this, I don't know this, but I do know Kp. And so this is a very simple, almost plug and chug type problem. I'm going to write my Kp expression. So, remember it's not concentrations. In this case, it's partial pressure. So the partial pressure of the ammonia squared over the partial pressure of the N2 times the partial pressure of the H2 cubed. Keeping in mind, I know what Kp is, right? It's right there. It's 1.45 times 10 to the negative fifth. They told me what that value was. I know the partial pressure of the nitrogen. That was also given to me in this problem. It was 0.432 atm. Again, I'm going to leave my unit out because I know it's going to be, unitless. Your Kp is unitless. I also know the partial pressure of the H2. It was 0.928, but I need to be careful and I need to cube that value. Okay, and it's this value that I am being asked to find. Right, so in that case, this is going to be my x. Let me clean this up just a little bit. It looks kind of funky. Okay, so in this case, I'm going to solve for the partial pressure of the ammonia, but that value is squared. Okay, so I have an x squared in here, and this is a one variable equation. I have one unknown, and so I should very quickly be able to solve this. So I'll kind of come up here. So of course my Kp is equal to x squared over this times this cubed, which is easily evaluated on a calculator. I got this. Okay, so that becomes my denominator. Of course, I need to clear my denominator, so multiply both sides by the denominator. Whoop. Okay, so it's going to cancel, leaving me with this times this, which of course I can evaluate is equal to x squared. I'm not crunching this on the calculator just for sake of time. I have it all solved out. So in this case, x squared is equal to this value, and you might get kind of excited and think, oh, I'm done. That must be my partial pressure at equilibrium, but keep in mind that's x squared. Okay, so I really just need x, so I need to take the square root. And then once I do that, I get a partial pressure of 0.0022 atm, which of course is equal to the partial pressure of the ammonia, because that's what x is. And so I have solved my problem. If you're unsure if you did that correctly, of course you can always take this number, plug it back in, for here, square it, divide by these, and you should arrive at a Kp value that's very similar to that, maybe slightly off only because of rounding, but it should be very similar. Okay, so when we have equilibrium data and we're asked to find, sorry, I was looking for my eraser, there it is. We're asked to find kind of a missing piece to the puzzle, so to speak. It's very simple, calling something an X because it's unknown, plugging in my Kp or my Kc, and going for it, being done. So it's quite simple approach to that problem. And we have done that back on the worksheet where we were, I don't know, it was like the Kc and Kp worksheet or something. We've done that before and solved for kind of an unknown value. Now, life changes slightly in this next problem when they withhold the equilibrium data. So this problem is going to take up quite a bit of room. So in this area at the bottom, if you think you're going to need more room, you might want to grab an extra sheet of paper. Okay, so here we go. A 1 liter flask is filled with 1 mole of H2 and 2 moles of I2. The equilibrium reaction is there. They give me Kc, so let's go ahead and write all that. So I have H2 plus I2, 2HI. They tell me that Kc in this case is 50.5. And the question is, gosh, what are the equilibrium concentrations of all three species, so to speak, at equal, whoop, that's a 2. Okay, so I have a kind of a 3-part question. I'm looking for 3 answers. The concentration of each of the 3 species in this reaction. So I know I have a Kc. I could go ahead and write an expression, but I'm going to be a little bit stuck because the data that was given to me in this problem is initial data. And we very well know that at this point, we cannot plug initial data into a Kc or a Kp. So hearing that initial word, we know we're going to need an ice chart. So we can go ahead and build that. And remember, if this is a Kc, the only thing that can go into the ice chart is concentration. We were given mole values, but we were also given a 1 liter flask, so the mole values are actually the molarities. So they tell me, let's see, they tell me I have 1 mole of H2, so 1 mole in a 1 liter container would be 1 molar of H2 initially, and then I have 2 molar I2 initially. Keep in mind this problem is asking me to find these numbers, right? That's the goal. If I can just find that, it'll be good. But I'm given nothing else, okay? So, of course, we do know that if I have H2 and I2 in my container, initially I have no product, right? Because that's at time 0. I do know that my reactants are going to have to decrease, as time progresses, and my product is going to increase, right? The only thing 0 can do is get bigger. But that's it. Normally in an ice chart situation, we have one number down here, and we backtrack and can fill in that change line, but I don't have any of that. So this problem forces me to use a variable to represent this change. So we're going to pick X. Seems to be our favorite variable. So I'm going to say that the change in the H2 is just going to be reflected by it's losing so much. Okay, I'm going to call it X. Remember, the change line is the line that is governed by the stoichiometry of the reaction. So if the H2 is decreasing by X because this is a 1, then the I2 is also decreasing by X because it's a 1. But the HI is increasing by double that amount. So the HI would be increasing by a factor of 2x. And then from there, I can come up with my equilibrium concentrations, but they're in terms of x. So 0 plus 2x, of course, is 2x. 1 minus x is 1 minus x. And 2 minus x is 2 minus x. So in all actuality, this is my answer, kind of, to my question over here. What are my equilibrium concentrations? Those are my answers in terms of x. But if I want to numerically evaluate this, I have to know what x is. So I have to somehow solve this for x. Okay, and we're going to do that with the only piece of this problem we haven't used yet, which is the Kc. So I'm going to jump down and write my Kc expression, which is, of course, products over reactants. And then I'm going to take this information, which of course are my equilibrium concentrations, but in terms of x. And I'm going to plug them into this expression. So, here we go. I know Kc, right? It's 50.5. I know that my HI concentration is being represented by 2x, right? But that whole quantity is squared. Okay, so I'm going to have to square the quantity of 2x. And then I know that my H2 concentration is being represented by 1 minus x. And I know my I2 is being represented by 2 minus x. Right, now this gets a little bit, messy. So we'll walk through, of course, all of this together. So let's see, 50.5 equals, again, the goal here, we're trying to solve for x. So 2x, the quantity squared, that would be 4x squared. This down here on the bottom, I'm going to have to FOIL. So here's where chemistry takes a big turn down the algebra path, so to speak. So if I FOIL this, I get 1 times 2, that's 2. Negative x times 2, so that's minus 2x. Let's see, 1 times negative x, so minus another x. And then negative x times negative x, which is, of course, plus x squared. Right, I can combine my x's, so I'll just jump down here. 50.5 equals 4x squared. So this would be 2, let's see, minus 2x and minus 1x, so minus 3x plus x squared. Hopefully you can still see. Yeah, okay. So I'm still on a mission. I have to evaluate this thing for x. And, okay, so it's messy. So it would be probably in our best interest to clear this of the denominator, so to bring that denominator up to, the other side. So I'll multiply both sides by, this is going to be hard to squeeze in here. So I'm going to multiply both sides by what's in the denominator so that this happens, right? And I'll write this out because I know this is getting crazy. So what I have is 50.5 times 2 minus 3x plus x squared equals 4x squared. Okay, so that's where I am right now. For sake of room here, I'm going to erase some of this so that I can, we can follow this whole thing. So give me 1 second. Okay, so where I am right now is right here, 50.5 times 2 minus 3x plus x squared equals to 4x. That should be 4x squared. I dropped a square. Whoops. Okay, there we go. All right, so that's where we are. And remember the goal, we're trying to find x, but I got a bunch of x's in a bunch of different places, so I'm still on my, mission of kind of combining like terms. I need to do some distribution over here on this side, so 50.5 times the 2 would be 101. 50.5 times negative 3x would be negative 151.5x, and then 50.5 times x squared would be 50.5 x squared equal to 4x squared. Okay, we're getting somewhere. And for sake of keeping this just kind of how my brain works, and I'll tell you about that later, I'm going to take the 4x squared to this side, so minus 4x squared minus 4x squared. Going to leave me with 0 over here. And then I have 101 minus 151.5x minus 46.5x squared equals 0. And some of you might be saying, oh my goodness, this is a quadratic equation. How in the world am I going to factor that? We're not going to factor it. The only way that we're going to be able to solve this is by using the quadratic formula, okay, to solve for x. And so this is a positive. Oh my gosh, I'm so sorry. Positive 50.5x minus 4x. Okay. So here's where I'm going to attempt to use the quadratic, okay? And let me do a couple things. Let me get rid of this. I'm going to flip this equation around because I think some of you know that the quadratic equation is ax squared plus bx plus c equal to 0. So I want my x squared term out in front. So I'm just gonna move these things. So my equation is gonna look like this: 46.5x squared minus 151.5x plus 101 equals 0. Okay, so, of course, with the quadratic, A is this number, B is this number, and then C is this number, right? And the quadratic equation is the one that some of you learned that funny little, whatever, memory trick too, but it's the one that looks like this. X equals negative B plus or minus square root B squared minus 4AC all over 2 times A. All right, and so what a loaded question, but the only way we're going to be able to solve this is by using the quadratic, okay? So, here we go. I'm going to come up top, I think. So, x equals, here we go, negative b. So, b is already negative, so it would be positive. So, 151.5. Remember, none of these x's come with us, just the coefficient. Plus or minus the square root of b squared. So, negative 151.5 squared minus 4 times the value of a, 46.5, times the value of c, 101. Woo! Over 2 times the value of a, 46.5. Okay, and now this is just about simplifying this and evaluating this for x. So here we go. So x equals, 151.5, sorry, I lost my train of thought, plus or minus the square root. And now let me see what I did. I'm just going to evaluate everything underneath the square root. Okay, so I'm going to take the negative 151.5 squared and then minus 4 times this. And when I did that on my calculator, which you want to be doing too, I got a value of 4,166.25, some change, whatever. And then over 2 times this number, which gives me a value of 93. Okay, from there I'm going to evaluate the square root. So x equals 151.5 plus or minus. So taking the square root of that number gives me a value of 64.55 divided by 93. And now this problem has become much more manageable. But I think most of you know that that plus or minus is going to give me 2 answers, right? So x could either be 151.5 plus 64.55 divided by 93, which is going to give me a value. Or x could be 151.5 minus 64.55 divided by 93, and that's going to give me a second value. So when I do that, I get a value of 2.32 as a possibility, and I also get a value of 0.935 as a possibility. So if you don't get these 2 answers, I want you to pause this and go back and check your math. Make sure you're not entering a sign incorrectly or something like that. But the 2 possible values of x are these 2 numbers. Okay, now the question is, well, which one is it, right? If it can technically be 2, which value of x is the one that I use? And if you're paying attention to what we did in that, remember, we're going back to this, that's why I purposely didn't erase it, the equilibrium line on the ice chart, only one of these values makes sense for x. And so if you're thinking about it and looking closely, x cannot be 2.32. And the reason is because if I took 1 minus 2.32 and 2 minus 2.32, I would get 2 negative answers. And there's no way I can have a negative equilibrium concentration. So there's no way that that's the value that I can use. And so this is the value of x that I'm going to use for this problem. So I'm going to just rewrite that over here. Now, just writing that on my paper, I have not answered the question, because remember, I was trying to find these 3 equilibrium concentrations, but all I have to do is take this value of x and plug it in. So the concentration of H2 at equilibrium would be 1 minus the value of x, which is 0.935. The concentration of I2 at equilibrium would be 2 minus the value of x, which is the same thing, 0.935. And the concentration of HI at equilibrium is 2 times the value of x, of course, which is that. So all I have to do is number crunch. I get a concentration of 0.065 molar for H2, 1.065 molar for I2, and 1.87 molar for HI, and this, whew, holy cow, is my final answer. Now, you could always check yourself. You could take these three equilibrium concentrations, rewrite your Kc expression, plug them in, and you should get a value of 50.5, give or take, of course, with the rounding. Now, disclaimer. The AP exam is never going to give you a problem where you are forced to use the quadratic equation, okay? Never. But I think it's still very important for us to walk through a problem like this so that you can be familiar with it, because your college professor will. There's a second quadratic problem on the back, or the last page, that is the same idea. It's an ice chart. You work your way through it. For sake of time and making this video extremely long, I'm not going to go through that solution key, but I will post that for you so that we can discuss that at another time. So give that a try on your own. See if you can get that last quadratic problem to work. And so that is how we can use Kc and Kps to determine equilibrium concentrations or partial pressures, whether or not we have equilibrium data to start with.